So, hi everyone, and welcome to my talk on how your brain is conspiring against you making good software. So, my name is Jenna Zeigen, and a little bit about me. So, I am an engineering manager at DigitalOcean, and if you're not familiar with DigitalOcean, we're a New York-based company that tries to take the cognitive load out of managing your infrastructure. I'm also an organizer of two New York-based JavaScript events, one of which is EmpireConf, which is happening next week in Manhattan. And I also am an organizer of Brooklyn.js, which is a monthly JavaScript meetup that happens in, of course, Brooklyn. So I know just how much effort it takes to pull off an event like this, so can we get a round of applause for all of the organizers here? Thanks. You might also know me as ZeigenVector on Twitter, and you can find these slides at that link. All right, so now the good stuff. So before I was an engineering manager, and before I'd written a single line of JavaScript, I studied cognitive science in university. And cognitive science is the study of thinking, decision-making, attention, vision, consciousness, and my personal specialty, human language processing. But if you ask me to sum up what I learned in those 4 years in one concise sentence, it would be that humans are predictably irrational, as psychologist Dan Ariely has said, and he has a book by that predictably irrational title. What this means is that we employ predictable tricks, patterns, and shortcuts that allow us to make more efficient decisions. But this fast thinking often causes us to be not so rational in our judgments, to make what two other prominent psychologists in the field, Amos Tversky and Daniel Kahneman, have called severe and systematic errors. And these errors are cognitive biases. But this is a programming conference and not a psychology conference, so why am I standing up here talking about our minds and the mistakes that it makes? Well, that's because, as the fine folks at And Yet say, software is about people. Software isn't just about code, it's also about humans. We as humans write software for humans and with other humans. So again, software is not just about the code. It involves a human element too. So my job as an engineering manager is to make sure that my team of humans is happy, healthy, productive, getting their work done, not fighting with other teams. So my team it's my product. So I started thinking about how I could apply my 4 years of cognitive science education to my job as an engineering manager. And I started thinking about these cognitive biases and how they and the other quirks of our mushy human brains affect us as we're making software in the environments that we're supposed to be making software in. Because even the most calculating software engineers is a human, and therefore subject to cognitive biases, no matter how much we think that we are immune to the irrationalities of humankind. So over the rest of this session, I will talk about these things all the way from being logical through assembling a team. So I figured we'd start off talking about logic because, logic is one of the fundamental underpinnings of programming. We have if statements, else statements, ternary operators, booleans, but computers can only do what humans tell them to do. And it turns out that humans aren't very good logical thinkers. One tool that psychologists use to test this out is called the categorical syllogism, and there's one right here up on the screen. A categorical syllogism is a logical argument beginning with two premises followed by a conclusion, and psychologists will ask, does the conclusion follow from the premises to test out how their participants are reasoning through these logical statements? So I'll give you a chance to figure this out for yourselves. So when psychologists asked participants, they found that 81% of people said, yep, the conclusion follows from the premises. 10% said something else wrong, and only 9% of people got it right, which is pretty bad. And reasoning about complex if-then statements isn't much better. A psychologist named Wason made this now classic 4-card task in which there were 4 cards, and on one side of the card there was a letter, and on the other side there was a number. And the participant's job was to evaluate the following rule. If a card has a vowel on one side, it has an even number on the other, and then asked what cards needed to be flipped over to check that this rule checks out. So I'll give you some seconds to think that over. So when this experiment was run, only 4% of participants got the right answer, which is to flip the A and the 7. And if you're stumped about why this is right, remember the rule says nothing about what consonants have to be paired with. But luckily there's some hope, which is that we get better when reasoning about concrete examples. So some scientists modified Wason's 4-card task to try out this more real-life statement, which is that if a person is drinking beer, they must be over 19 years old. In this case, 73% of people got the right answer versus the 4% in Wason's original 4-card task. So when we inevitably make a mistake in our code, because after all, we're humans, we're going to have to end up debugging that code. But as computer science celebrity Brian Kernighan once said, debugging is twice as hard as writing the program in the first place. And I think there's some cognitive science things that are getting in our way and making this difficult. So one of these things is that we fall prey to the confirmation bias, which is that we have the tendency to search for, interpret, favor, and recall information so that it confirms our pre-existing beliefs or hypotheses while giving disproportionately less consideration to alternative hypotheses. And scientists found this. So again, Wason presented subjects with a series such as 2, 4, 6, and told the participants that the trio conformed to a specific rule. And their job was to figure out what the rule was by asking if other trios of numbers conformed. The rule in actuality was quite simple, just that the numbers had to be in ascending order. But people ended up having a lot of trouble. This is because they would just ask questions that confirmed their hypothesis. So they saw this trio, they're like, oh, it's gotta be that the numbers have to be even, and then they go up by 2. So they would just ask the scientists, hey, does 8, 10, 12 conform to the rule? And they'd be like, yep, thumbs up, and then they would assume that the rule was the initial thought that they had. Because they didn't ask disconfirming questions like, does 3, 2, 1 work? How about 2, 2, 2, 2, 3, 4, 1, 3, a million? They didn't get other evidence that would help them recompile their hypothesis and come up with the actual correct answer. So taking this back to writing software, like, what does this mean for testing our code so that we don't end up with bugs in the first place? We even tend to scrutinize disconfirming evidence, trying to find flaws or ambiguities, blaming, say, a bug in the library or someone else's code. Even when the facts are clearly stacked up against the belief that we hold to be true, we often throw out those disconfirming facts. And this effect is stronger for emotionally charged issues, such as when your code is wrong. Another thing that's getting in our way is that we often have no idea we're going to solve the problem soon, even 30 seconds before we crack it. And this frustration feeds back and makes it harder and harder for us to focus on the task at hand instead of getting all up in our head. So to test this, scientists gave subjects insight problems, kind of like word problem brain teasers. And as the participants solved the problem, the psychologists asked them to rate their progress in terms of warmth. So how close do you think you are to solving the problem on a scale from 1 to 10? Initially, participants gave ratings of 1 to 2, and then their ratings abruptly spiked when they got an answer, regardless of whether it was correct or incorrect, indicating that they didn't really realize that they were close to solving the problem when they, in fact, were. Also, breaks are really important. They allow us to forget things that are holding us back. And psychologists found this when they gave participants puzzles to solve, as well as some misleading hints about the solution. So one group of participants had a minute to solve the problem without breaks, and another group had 30 seconds, had a short bit of time in between, and then were given another 30 seconds to solve the problem. It was found that the interrupted group did better, because they were less likely to remember the misleading clues. We also have a tendency to approach a problem in a particular way, and this is called our mental set. And our mental sets are shaped by our experiences and habits. So if we wrote the code, when we go back to try and debug it, we're probably going to end up thinking through the problem in the same way as when we initially wrote it. And it's going to be harder to think outside the box and squash the bug, especially if the bug is on a more conceptual level. Like, I know I'm very guilty of making like really silly errors, like substituting a single equals when it should be a triple equals, and those are like rather silly, simple bugs. But when the bug is on a much broader level, it's even that much harder to solve the problem. And just a note here, I find that pairing unsplashing bugs is a good way to kind of circumvent this cognitive bias, because your colleagues are most likely going to have a different mental set than you and might be able to help steer you in a better, more fruitful direction. Bug squashing is a form of problem solving, and problem solving is often linked to creativity. But what exactly is creativity? Well, psychology says it's really nothing special. It's just when all the sum of your experiences, memories, training, and motivation come together in the right way. It's all about associative memory. All right, so we're at the point where we're working with other people to maybe squash bugs. Maybe you have colleagues at work, or maybe you're other open source maintainers. So you're gonna have to try and read someone else's code probably, or even if you're working by yourself, you might want to introduce a library into your code that you have to go through and read to figure out how something works. But this is going to be pretty challenging because, again, the writer of that code is probably going to have a different mental set than you do. We also tend to prefer things that we have made or assembled ourselves, and in the software field, we often call this not invented here syndrome, but psychologists have a different name for this, which is the IKEA effect. And this is named after the experiment that some scientists ran, in which they asked participants to assemble IKEA furniture, build Lego contraptions, and fold origami. And then they were asked how much money they would pay for their creations, as well as for experts' creations. And it was found that the participants were willing to pay a similar amount of money for the well-crafted experts' creations as they would for their dilapidated amateurish work. And while this experiment was just about money, I think it's fair to extrapolate this to value in general, that we tend to value the things that we made versus experts, even if the experts have, say, been in other people's production, or have all the edge cases tested out, or just been contributed to by more than one person. So working with other people, you might have to, tell someone else how long you think it's going to take to get that task done. But it turns out we're really bad at that. We're really bad at estimating how long it's going to take us to do something. And as an engineering manager, this is a fallacy near and dear to my heart, because I also end up playing the role of the project manager, and I want to know how long it's going to take someone to do something. So this is the planning fallacy, and it really gets me. And this fallacy was demonstrated in an experiment in which 37 psychology students were asked to estimate how long it was going to take them to finish their senior theses. The average estimate that they gave was 34 days, with the actual average being about 56 days, with only about 30% of people finishing in the time that they said it was going to. And this phenomenon occurs regardless of if we know that past tasks of a similar nature took longer to execute than we thought. And also apparently, these are psychology students, so they probably knew about the planning fallacy, and that didn't help them either. And this only happens for our own tasks, whether individual or group tasks. For other tasks that we have no involvement in whatsoever, we tend to show a pessimistic bias. We think it's going to take other people longer to get their work done than it actually will. The planning fallacy is part of a larger bias called the optimism bias, in which we think that bad things are more likely to happen to other people than to us. And this is seen in a wide array of situations, not just in planning your work. For instance, we think we're less susceptible to crime than other people, less susceptible to the whims of the stock market, less likely to get sick, when in actuality, we're not special and the numbers apply to us just as much as they do to anyone else. We're also loss-averse, generally. When thinking about the cost of a decision, we tend to focus more on what we will lose than what we will gain. And this is especially important when it comes to the sunk cost fallacy, which is that we're often so worried about wasting already invested resources that we don't consider the loss of continuing to invest more. So for instance, if a project seems to not be going in the direction that we think that we were originally hoping, we're often weary of scrapping the project because, hey, we put so much time into it, we might as well see how it pans out. So you leave the planning meeting and you go back to your desk where the person next to you is on a Google Hangout with the person next to them. You might be able to tell I'm not such a fan of open offices, so I'm going to start with something that doesn't initially seem to help my case, which is that we're actually pretty good at filtering out unwanted things. And this is called selective attention. And this was found in an experiment that psychologists like to call a dichotic listening task with shadowing. So what's happening here is we have a participant and she hears one stream of speech, like I love JavaScript, in one ear, and in the other ear she hears kitty videos are great. And her job is to shadow one of the speech streams, so I love JavaScript, and just not pay attention to kitty videos are great. So it turns out that she's going to have very little memory of the semantic content of kitty videos are great, but she's going to notice that it was speech or not. So in the actual experiment that was run, participants didn't even notice the switch from English to German. But it turns out that we are not totally oblivious to the stuff that we're ignoring. We do notice and remember physical attributes of the sounds, so we're generally able to remember if the unattended channel, so what we're not repeating back, is speech or not. So if you're focused on writing code and there's music playing, you'll notice that there's music playing but not really be comprehending the words. However, if there's something salient, like someone says your name, even if you're not paying attention, your ears are going to perk up and you're going to notice that someone said your name, and this is called the cocktail party effect. And this suggests that we're processing all of the stuff that we're ignoring before throwing it out. So we are actively ignoring and actively paying attention to everything that's going on around us. So just because we're good at selective attention doesn't mean that it's good for us. We're putting in active mental effort that could be to blocking out what we're not supposed to be paying attention to, that could go towards solving a difficult algorithm that you're trying to figure out. So we have a limited supply of mental resources that we often don't have the budget to do more than one thing. So you're probably not going to be able to keep writing that difficult method that you're trying to figure out when your engineering manager and your product manager are having a conversation 10 feet away about how they finally stopped succumbing to the sunk cost fallacy and they're scrapping the project that you're working on. So in short, we are helpless to the processing power of our brains. Our brains do things automatically in an attempt to be efficient. And the effects of this can be seen in this fun thing, which you might be familiar with if you had an email account anytime around the early 2000s when chain letters were popular. So this is actual real science. It's called the Stroop task. And the idea here is to say the color that the word is written in and not the word itself. And this is quite difficult, even if you have full color vision. So this is easy if you have full color vision. This is easy if you can read. But this is challenging. And the leading theory about why this occurs is that reading is an automatic habitual process, whereas recognizing a color isn't. So while we don't need to be actively paying attention to read words, so reading doesn't need controlled attention, it uses enough resources to reduce the amount that we can dedicate towards processing colors. All right, so I'm about to get into the more human, feelingsy side of all of this. I think it's important that you have a good sense of how good you are at something to be able to improve and to get better at your craft. And something that's getting in our way about, in this case, is what's called the Dunning-Kruger effect, which is that unskilled people think that they are better at tasks than they actually are. And this was inspired by the case of a man who robbed 2 banks after covering his face with lemon juice. Since lemon juice can be used as invisible ink, he thought it would cause his face to be invisible on the security cameras. Oops. Dunning-Kruger is an example of a larger phenomenon called illusory superiority, in which we overestimate our own abilities and qualities and underestimate our negative traits. This was found in a survey of the faculty of the University of Nebraska, in which 68 of these teachers rated themselves in the top 25% for teaching ability, and more than 90% of people rated themselves as above average. But that just simply doesn't math, right? The way that averages work is 50% of people are above average and 50% of people are below average. So how is this getting in our way? Well, you're not going to make good software if you don't realize how much more you have to learn. And perhaps something that will make this a little bit easier to swallow is the fact that, like, just because you're below average doesn't mean you're bad at what you do. You could be below average on your Olympic team and still be one of the best people of in your field. Also, we're all below average in something, right? Like, I'm below average in height, and I try to rock that as much as I can. So the flip side of this is that skilled people often underestimate their abilities and think that tasks that are easy for them are easy for others. So if you've been writing code for a long time, you might forget what it's like to be a beginner. And this is bad because it might cause you to be less empathetic towards individuals who are, say, like, just starting out writing code, right? Your job as a senior engineer on a team is to mentor the folks that are less experienced than you. But if a less experienced engineer comes to you and is like, I need help on this, and you're like, oh, it's really easy, you just do it this way, that less experienced engineer might not come to you with questions anymore, and they might not end up writing the best software they could be writing, and they might also not ask the questions that you just don't think to ask anymore that will make everyone's software that much better. This could also manifest as imposter syndrome, in which people think that their accomplishments are the result of luck, timing, or deception, that they don't deserve the things that they have achieved. And some studies suggest that this is particularly common among high-achieving women, but I've seen this happen across the board. Like, some of the best programmers I know suffer from imposter syndrome, and it's not helping them write the best software that they could be writing. All right, now we're going to talk about how our cognitive biases get in the way of us assembling a team. And some of these might fall under the umbrella of unconscious bias. And this is something that has been more popular to start talking about in tech. And I'm really happy that this is something that's gaining more popularity to talk about. So the first thing that's getting in our way in assembling the best team that we could be assembling is that we tend to favor members of our own in-group. So this is particularly bad in the popularity of referral bonuses. So you refer your friend, you get money if they get hired. But we tend to refer people from our social circles, and our social circles tend to look like us. So, my job as an engineering manager is to grow my team, and if I were just to hire people that look like me, I would end up with a team of white women, which isn't good either. We also tend to attribute situations to other people's character rather than to perhaps external factors. And this is called the fundamental attribution error. The classic example of this is, so you're like driving down the road and obeying all of the traffic laws, all of them, and someone like races past you, they like run the red light, and you're like, ugh, what a jerk. When in actuality, they have a loved one that they're rushing to the hospital, and all other times, they are also driving the speed limit. But at that point, all they're thinking about is their loved one and not the speed limit. So it's important to have empathy for the external factors that is motivating someone to make the decisions that they're making. This error also occurs and applies similarly to groups in what's called the group attribution error, which is that we tend to believe that attributes of a group member reflect the entire group. And this is illustrated quite nicely by this XKCD cartoon. So on one side, you see two men, one of whom is apparently bad at math. And his friend is like, wow, you in particular suck at math. On the other side, we see a man and a woman, and apparently the woman is not that great at math. And the man who she's doing her math with says, wow, all girls suck at math. Not just you, all women must suck at math. So why does this ring so true? Well, studies have shown that the group attribution error is stronger in perceptions of groups that are different from our own and disappears when thinking about our own groups. So in other words, decisions made by those in our own group are the result of structural constraints, but decisions made by people in other groups are the result of their personal attitudes. So perhaps, maybe it's not that certain groups of people don't want to be programmers, maybe there are structural forces making it harder for them to do so. Something else that's getting in our way is the availability heuristic, which is that we tend to rely on examples that come to mind when evaluating something. So the classic example of this is why we think that plane crashes are so much more common than they actually are. It's because we hear about plane crashes on the news. Those are newsworthy events. But a plane successfully making it from point A to point B is not a newsworthy event, so we never hear about that. So we think that plane crashes happen a disproportionate amount than they actually do. So taking this back to tech, if all of the prominent members of a community look one way, if everyone you see on stage looks a certain way, if everyone you see contributing and maintaining open source projects look a certain way, you're going to start to think that those are the only people who are allowed to do that, who are good enough to do that, when that's just certainly not the case. And while we do have a problem with everyone looking, a lot of people looking the same way in the tech community, I think if we start to be more aware of this problem, we might start to put a dent in that a little bit. We also fall prey to the representativeness heuristic, which is that we assume group members will resemble the prototype for that group and vice versa. Essentially, that categories are relatively homogeneous. So if someone is a software engineer, we expect them to have the traits that we associate with a software engineer and vice versa. This heuristic leads to several biases, such as my personal favorite, base rate neglect. So in an experiment that Tversky and Kahneman ran, they told participants that there was a group of 100 people in which there were 70 lawyers and 30 engineers. They then gave descriptions of those people and asked if they were more likely to be a lawyer, which there were more of, there were 70 lawyers, or if they were more likely to be an engineer. There were only 30 engineers. And participants often said that someone who sounded like an engineer was more likely to be an engineer, even though they were only 30% likely to be an engineer based on math. I've seen this come true at programming events. I've gotten it, and I've heard countless stories of my friends who they're at a programming event, so it's likely that someone who's at a programming event is a programmer, or at least is aspiring to be a programmer. But we often get these questions like, hey, are you here with your significant other? Are you a recruiter? Are you a designer? And like, recruiters and designers and everyone else who's not a programmer, they are also essential for us making the best software that we could possibly be making. Like, I couldn't do those jobs. But I just want it to be okay to be a programmer. I'm at a programming meetup. I want it to be okay for me to be here. So you might, thanks. So by now you might realize that I'm talking about diversity. So like, why is diversity important, right? Like, I think I've given some hints from the cognitive science point of view about why we want to create diverse teams. It's because, remember, that creativity is about associative memory. So the wider array of people you have on your team, the wider array of backgrounds, experiences, education, and interests you're going to have on your team. So you will have a wider collective associative memory, and therefore your team will be more creative overall. All right, so that was a lot to take in. So like, how do we get better at all this stuff? Well, first off, like, don't fault yourself. Your brains are like literally programmed to be this way. Your brains are programmed for efficiency because like back in the day, our job was to stay alive. And thinking quickly, thinking on your feet, using these heuristics, these biases, they were designed to keep us safe, to keep us alive and keep our families alive. So we evolved this thinking fast system. But we also have a thinking slow system, and this is what we use every day for our programming jobs. You know, our job is literally to sit and think. We think through these hard problems, we think through how to like sort an array or whatever. And this like, if we just sat for a few more seconds to think through the decisions that count, like if you're going to hire that person, we might end up making a software that's just a little bit better than the software that we're already making. Right, thanks for listening. You can find the slides at that link and tweet at me at ZeigenVector or find me in the hallway if you have questions. Thank you so much.